din Folke. So, good morning everyone. I wonder if people hear me. I don't think so. Wait. Wrong direction. Now, good morning everyone. I hope that everyone can hear me. And welcome to today's dissertation, which is a bit of a special dissertation, of course, for us and probably for you too. It's the first dissertation that we have online here at this department. And even though I have to say it feels a bit unaccustomed to be here with such a small audience. We are, there's an audience of 5 people here and about 5 technical staff. But it's also quite nice to see that there's so many people participating online. And you can see those yourself, and there's also probably, I would guess, almost just as many watching the YouTube broadcast, even though the YouTube broadcast will be closed after the presentation when the opponent takes over. And also to say something about the pandemic and the situation we have, I'm quite happy that that happened now and not 10 years ago, when I think this would have been so much more problematic. And even though we have technology here that seems to work fine, technology, as you know, also never works really by itself. So first of all, I would actually like to say thank you to everybody that has arranged this and assisted us. There's actually quite a lot of job behind, not from me, but from a lot of other personnel, which some are here, some are online. So thank you, for example, you Åsa that I've seen that are with us, has done a lot of work. Sofia, Christine, Jonny, and a lot of other people that has made this possible. And I think that this might be also a new standard, whatever happens in the future with diseases and things. That at least some people, or a lot of people, will participate online. So then, as you know, this is Xiaotian Li's big day, or Tian as he prefers to be called here, since non-Western people can pronounce his name properly. And then for you who don't know me, I am Johan Sidén, and I had the pleasure of working with Tian from all the way actually from his master thesis and project course before that. So we've been working quite closely for quite some years. And that means that also for me it's quite a big day when you work closely with someone for a long time, and I'm really looking forward to this day. And together with us we have also had Henrik Andersson. I think he can stand up, who has been the co-supervisor of Tian, and I would say can also be held responsible for quite a large part of this work.
Hello,
so,
hello.
Yeah, that's it. And yeah.
Continue.
Then with us today we have 4 prominent, not guests, but participants that is not from Mid-Sweden University, but is very important for this dissertation. And that is the main opponent, who is maybe the most important person, along with the respondent. That is Professor Leena Ukkonen from Tampere University, who is perhaps the one in the world that has published most in the field that relates to Tian's work. Then we have a grading committee, who are actually the ones that, yes, nice to show yourself, Leena. And the ones that actually decides on the grade, just like it sounds. That's the grading committee acting like a jury. When the opponent, if you take some resemblance to court, the opponent is more like an attorney, questioning and interrogating, even though we encourage more of a discussion. And the grading committee is assembled by people that both knows the field and run really well the exact field, and most of all have a large experience from general scientific work and what it takes to become a PhD or the requirements to get it. So we have Professor Daniel Rönnow from University of Gävle. Maybe you can show yourself, Daniel.
No, all of a sudden I get. I hope you can hear me.
We hear you loud and clear.
Yeah,
okay.
but now it says you cannot start your video because the host has stopped it. So something has happened on your side. So I don't know.
Then I know.
Okay, now I can start my.
Thank you
for saying hi.
Oh,
now you see it. Yeah.
Okay, so now I was allowed. Yeah. Okay, hi, I'm here.
Then we have Associate Professor Jonny Johansson from Luleå Technical University. Let's see if we can allow you to.
Yes, good morning everyone.
Good morning, Jonny. And last but really not least, we have Dr. Sari Merilampi from Satakunta, University of Applied Sciences in
good morning,
Tampere,
everyone.
Finland. Good morning, Sari. And now I will soon hand over to Tian to give his presentation, but first I would like to try to share and show today's schedule, how we are imagining these days to be. Let's see. A bit lack of room here. No, where can I? Oh, just one moment. So, I think you can see the screen. Is it shared?
Yeah.
Yeah,
No,
good.
No?
Oh, here. Now the screen is shared, right? Yeah. So the dissertation will start with me, of course, opening the session as the chairman. And I can have my laptop there. Please give me my laptop. And just as follows here, the opponent, Professor Ukkonen, will take over and give a very short presentation about the more general field that is a bit above and around Tian's work. And when Professor Ukkonen is done with that, we will hand over the word to Tian to present his work, the thesis, the scientific view of his work, which will last likely to maybe 30 to 40 minutes. After that presentation of Tian, we will have a short break. The YouTube broadcasting will end, and you will have maybe some time to grab some coffee and go to the bathroom or so. And we will have some technical rearrangement here, and then we will see waiting room. Oh. Then the opponent will take over, and the opponent will have a discussion with Tian with regards to the thesis for actually as long as she wants to. There's no one that can say that the opponent should continue asking questions or should stop asking questions. But when the opponent feels that she is satisfied or exhausted, that there are not more things to discuss, the word is left to the grading committee. And the grading committee will ask a few questions each, maybe 5 to 10 minutes. But it's also up to them. We cannot say that, we're not allowed to say to them that we cannot ask more questions now. And when the grading committee is done, then you, the audience, the participants here, are encouraged to ask any questions that you wonder about Tian's research work, the scientific view he has, and so on. And we encourage you then to use the raise the hand function in Zoom. You can write your questions in the chat, or you can ask them orally by just turning your microphone on. And when everybody feels happy with their questions, and we realize that there's just silence in Zoom and in the room, we will have a bit of a longer break. That will take maybe 20 minutes, maybe a bit longer, where I, as a supervisor, and the co-supervisor, the opponent, meets with the grading committee to discuss what has happened today and what we think about the thesis. And that is where the major decision is done. So the grading committee, not the opponent, not me, the supervisor, not the co-supervisor, but the grading committee, those three persons will make a decision whether they think this work pass the requirements for a PhD title, or if there is a need to go back and do more research and have another scientific view of these things. Then we will return to this Zoom meeting. We will have this meeting in a separate Zoom room, and I encourage you to not leave this Zoom room because you will not be able to go back. But when we had this meeting, we will return to this room, to this Zoom meeting, and the grading committee will deliver their answer to Tian. And then, if it happens that the decision is positive, we also encourage you to turn on your cameras on, your microphones on, which means that you will also be allowed to do it, which you will are not now. And if you want to pass your condolences or greetings and maybe have a toast with Tian. There's not any real timeline for this by definition, but the whole thing should last. It's common that it lasts maybe 2 or 3 hours, not so much more. And with that said, I would like to turn over to Professor Ukkonen to give a short overview of this field. Thank you. Okay. Oh, okay, stop sharing.
Could I get the screen sharing enabled? Now it seems to be disabled.
Give us a minute.
Now you can share, Leena.
Okay, thank you.
Thank you also.
There still seems some issues, so do you, Johan, have the presentation there, which you could share through that?
Yes, we have it.
Yeah. Maybe that's faster.
Then I can take over. So.
Yeah. Don't forget to share screen.
Yeah. Let's see. Okay, and just tell me when to flip.
Yeah.
Okay,
yeah.
Go ahead.
Oh, thank you. Yeah, thank you so much. And first of all, thank you for this invitation to act as the opponent on this dissertation. So the area of this thesis is definitely very interesting and very orientated towards future electronic systems, and it deals with very important area to enable using different materials in electronic systems and to provide future sensor systems, different environment integrated systems. So this is really, really interesting work, and a lot of work has been done to to achieve this thesis we are discussing about today. And about my background, so I have about 15 years of experience with RFID systems, antennas, and different materials. So for me, this was also very, very interesting thesis to get familiar with and to be the opponent in this thesis. And I'm planning to share some of the work we have done in recent years on this area, which is well, quite closely related to the topics we are talking today. So can I please get the next slide? So we have been working on different RFID-based sensors, and different manufacturing methods. So here you can see some of inkjet printed gas and moisture sensors based on both UHF RFID with chips and also chipless RFID. So here, these both have been fabricated with inkjet printing technique and conductive silver inks. So different materials and manufacturing methods, they will enable different types of environmental sensors for the future. And can I please get the following slide? And also what was also dealt with in this thesis as well was the aspect of wearable RFID systems and wearable electronic textiles. So that has been one of the main research areas what my team has been concentrated on during recent years, and especially how different materials and manufacturing techniques can be utilized to provide clothing integrated RFID tags and sensors. Can I please get the following slide? And also one aspect which was also very excellently dealt with in this thesis work was how to mount the electronics components with different materials and on different substrates and surfaces. And that is also one area which we have also been concentrating on, especially with the textile electronic systems. So how to reliably attach the components and also kind of maintain the wearability and flexibility of the systems. And for that, we have used different systems and techniques. So here is one example of RFID tag and RFID chip attached on a textile substrate with direct write dispensing and silver paste. And can I also get the next slide, please? And here are more examples on textile integrated interconnections. So here they have been done with sewing techniques and like conductive threads, so with embroidery techniques. So this is also one example of material combinations we have utilized in our research work. And these aspects were also dealt with in this thesis. So, well, kind of as a general conclusion, I have already mentioned that this thesis work we will discuss today is very timely and provides important aspects for future electronic systems. So here in this thesis, the objective was to provide a systematic approach on how to implement large area electronic devices which comprise both digital and analog signals using non-conventional flexible materials and flexible circuit technologies. And there was a significant number of non-conventional materials and fabrication techniques which have been very carefully studied and analyzed, and also how to mount the components on these novel surfaces using the novel materials and methods. And kind of as a testing system, 2 types of UHF RFID systems were utilized to kind of provide practical insights and proof of these techniques. So this was kind of my starting and viewpoint on this thesis, and I look forward very much to discuss with the candidates a bit later. So thank you.
Thank you very much for that presentation, Leena. Now I will give the word to the respondent. Welcome, Tiano.
Yeah.
All right, can everybody hear me? Good morning and welcome to this seminar. And I would like to say thank you to Johan and Professor Ukkonen for the nice introduction. Now I'm taking over. I'd also like to thank you all for being here with me and for all those people who are watching this online. And thanks for joining me at this very special and strange period of time. And I would like to take this opportunity to summarize and present my work during the past 5 years. And today we're going to talk about how to achieve large area electronic systems using non-conventional substrate and conductor materials. And before we go into the presentation, I would like to remind you guys that there are some mistakes in the printed thesis, and they are listed here. And if you need a copy of this, please contact me later. I will send you a PDF file. And the presentation follows this outline. And first, I would like to give an introduction of flexible circuits, very general. And then we move to the motivation and the significance of this research work. And then we talk the details about implementations, characterizations and results of materials and fabrications, surface mounting techniques, and large area electronic systems. And then I will end this presentation with conclusions and future works. Flexible circuits, also known as flexible printed circuit boards, were originally developed in the 1950s for interconnecting rigid PCBs. An example is shown here, where a piece of flexible circuits is connected to the edge of a rigid PCB. And flexible circuits are widely used in today's electronic devices. An example is shown here that this is a camera for smartphone, and it is connected to the motherboard of camera via one piece of flexible connector. And flexible circuits are commonly made from copper foils laminated on polyimide substrate and then followed by chemical etching process. And for this type of circuits, the main circuit functionality are implemented on the rigid PCBs, which means that the functionalities of flexible circuits are only limited to connectors. With the developments of this field, that flexible circuits, that hybrid flexible circuits with SFNI components mounted on are now capable of implementing electronic systems with much more complicated functionalities. An example is shown here. On these flexible circuits, you can see there are a lot of components mounted. And besides the functionality that we can have more material options that are less conventional than copper, polyimide, and rigid laminates such as FR4. These materials include conductive inks, different mantle foils, substrates such as polymer, cellulose, and textile. Many of these materials have advantages such as organic, lightweight, low cost, and environmentally friendly. In addition to material options, the fabrication methods for flexible circuits are also versatile, that we can choose different fabrication methods based on the material we have. For example, we can apply chemical etching on mantle foils and printing techniques for conductive inks, such as screen printing here and inkjet printing as illustrated here. And if we want to apply conductive inks over a very large area, we could also choose coating techniques. Flexible circuits can be fabricated from very high speed, such as roll-to-roll and sheet-to-sheet. And roll-to-roll process is presented here, that this is when we were manufacturing some of the flexible circuits in one of our partner companies. Because of these features about flexible circuits, it is believed that one approach towards large area electronics is to use non-conventional materials and techniques that are related to flexible circuits. So that is also the main goal of this thesis work, is that we want to bridge these three items. And the main significance of this work is that this work provides guidelines and systematic approaches from non-conventional materials to large area electronic systems. And with the development of this work, the following novelties will be presented. We will present new material combinations for flexible circuits, and we will also present fabrication method to achieve low DC resistance when making tracks from conductive inks. And we will also cover new surface mounting techniques. And in the end, we will present large area electronic systems that integrate both digital and analog signals made from non-conventional materials. The overall approach for the thesis work, I divided into 3 steps, where the first step is materials and fabrications, where a sub-goal is to achieve low DC resistance tracks when using conductive inks. And with the circuits fabricated, and then we move to step number 2, which is to implement hybrid flexible circuit systems by developing surface mounting techniques. And the step 3 will use the outcomes from step 1 and 2, and which purpose is to achieve large area electronic systems, where I will introduce 2 RFID reader antenna systems. And for each step, there will be corresponding evaluations at the characterizations. And you will see this flow chart multiple times throughout this presentation to remind you guys where are we. And now let's take a look at step 1. The step 1, materials and fabrications. First, I would like to show you a list of the materials and fabrication methods that we have been used. And for conductor materials, we used silver flaking with silver particle size within nanometer range, and with a micrometer range. And then we also used silver nanoparticle ink with particle size of nanometer range. And we also used aluminum and copper foils. And for substrate materials, as we can see that paper-based substrate is a popular choice for this thesis. And we, in addition to paper, we also used one nonwoven fabric and polyimide. And different fabrication methods were applied to these materials. And we applied additive fabrication methods, such as screen printing and inkjet printing on conductive inks. And we applied a subtractive method. In this case, we used chemical etching to the mantle foils. There are 2 methods developed in this thesis with the purpose of to achieve a low DC resistance in conductor tracks when using conductive inks. The first method is to achieve a very high dry film thickness when using a silver flake ink. And we applied screen printing techniques to this ink and printed a total 6 layers of inks on the same location. And this photo here is a printed coil that was manufactured using this method. And the results showed that the dry film thickness of this coil has reached 42 micrometer with 6 layers of coating. That is a significant increase compared to only 1 layer coating, which resulted only in 11 micrometer. And as a result, the DC resistance of this coil dropped from 25.4 ohms to 3.8 ohms. The second method is to apply a screen printing technique on a silver nanoparticle ink. The objective of this method is to achieve a higher dry film thickness for a single layer coating than inkjet printed tracks, which is commonly only around 1 micrometer with a single layer. And in the meanwhile, we also would like to maintain the low resistivity advantage in silver nanoparticle inks. And we have applied this screen printing technique with a silver nanoparticle ink onto different substrates, which the results showed that an average of 3.6 micrometer dry film thickness was achieved for substrates without coatings, and an average of 7.3 micrometer for substrate with coatings. And these are an example of the tracks made from this fabrication method. And we also did current carrying capacity to the tracks made using the technique using the method number 2. And the reason why we do this is because we would like to investigate the possibilities for ink-based tracks to be used as the main conductor material in high current systems. And this test was conducted according to international standard IPC TM 650. And the results showed that we have the current carrying capacity between 2.2 to 3.5 amps on a 5.0 millimeter wide track were achieved, where the highest capacity was achieved on photo paper, and followed by tracks printed on polyimide and coated plastic and uncoated plastic. The result of this test showed it is possible to use conductor ink tracks in high current systems. However, these curves here still shows that the temperature on the conductor still rise higher than copper-based conductor. So it is still quite challenging to replace traditional copper conductor in high current systems. And also I would like to highlight some of the flexible circuits that we have fabricated. As we know that the conductive inks have resistivities that cannot be ignored. So in that case, we directly apply mantle foils on paper and textile substrates to form high performance paper and textile based circuits, where we have manufactured 3 types of circuits. They are made from a copper paper, aluminum paper, and aluminum and fabric. And it's worth to mention that these circuits are fabricated through high-speed roll-to-roll fabrication methods. Now, that was step 1 with the circuits fabricated. Now we move to step 2, when we will talk about surface mounting techniques. And the reason why we develop surface mounting techniques, because we would like to bring new solutions to enable hybrid electronic systems made from non-conventional materials. In that case, we could combine the advantages from both printed electronics and the silicon-based SMD components. And we have developed the following 4 surface mounting techniques using low-temperature soldering paste, isotropic conductive adhesive, anisotropic conductive adhesive, and a special method to mount components onto aluminum conductor in this thesis work. In addition to the surface mounting techniques, we also came up with a comprehensive set of characterization methods where we measure the contact resistance, component bonding strength, and we inspect the cross sections of the mounting joints using an scanning electron microscopy. And we also did assemble component binding tests to study if the assembled circuits are suitable for systems that require bending. And in order to show that the surface mounting techniques and flexible circuits can be used in forming functional electronic systems, we implemented NFC tags with the relative humidity sensing functionalities. With that being said, the first surface mounting technique is to use a low temperature solder paste. The reason why we developed this is because we would like to bring new solutions towards paper-based hybrid electronics and also avoid high temperature when using traditional soldering method. And the soldering was performed at a temperature of 138 degrees, and we evaluated both hot air soldering and reflow oven soldering. And we applied this technique to the following 3 types of circuits. The result of the surface mounting techniques are compared to components soldered on rigid PCBs, which will, as a reference, which is shown at the last row here in this table. Due to the results, we could recommend that components soldered on circuits made from silver flaking and cardboard paper and copper and paper circuits have low contact resistance, and the component bonding strength have achieved respectively 13% and 28% to components soldered on rigid PCB. And the components soldered on silver nanoparticle ink and photo paper showed high contact resistance, which was because thermal expansion mismatch between the solder paste and the nanoparticle silver track and the photo paper coating material. In that case, we do not recommend this method to be used in implementing electronic systems. And here we showed 3 NFC tags that are fabricated using these materials and using this low temperature solder paste technique, which the first and the third tags can communicate with NFC readers successfully. The second surface mounting technique is to use an isotropic conductive adhesive. We developed this because we think it is an universal solution to hybrid flexible circuits because it has a milder curing condition than low temperature solder paste. And because of that, it is applicable to a wide range of materials. And in this work, we used an adhesive that's based on silver particles, and we apply this technique to the following 4 types of flexible circuits. The result showed that we could recommend to use this surface mounting technique to mount components on copper paper circuits and aluminum polyimide circuits. The contact resistance achieved on aluminum paper and aluminum nonwoven was high. This was because during the fabrication process, a layer of adhesive remained on top of the aluminum foil, which was difficult to clean because the surface roughness of the aluminum foil we use is high. So it trapped a lot of adhesive, which means the surface of this aluminum foil cannot contribute as many electrical contact points as copper. So that's why it's not recommended to apply to mount components using this technique on aluminum paper and aluminum nonwoven circuits. And the component bonding strength of these achieved on these four circuits are between 6 to 27% to components soldered on rigid PCBs. And the same NFC tags with the same functionality were also implemented using the first 3 types of circuits, and they can all successfully be read by NFC readers. The third surface mounting technique is an anisotropic conductive adhesive. I would like to highlight this technique because it is a fully automatic component mounting process. And the same as isotropic conductive adhesive, it is a universal solution to hybrid flexible circuits. And it can be applied to a wide range of materials. And this photo shows, this photo was taken at one of our partner organizations when we were mounting components using automatic component mounting machine. And this photo is what's inside of this machine. And we used one adhesive that's based on silver and nickel particles. We applied this technique on the following 3 flexible circuits. The result showed that it is recommended to apply this technique to mount components on copper and paper circuit. However, due to the problem of aluminum conductor, as I explained before, it was not recommended to mount components on aluminum paper and aluminum nonwoven circuits. And the component bonding strength are achieved between 26 to 34% of soldering on rigid PCB. As we can see, this method can contribute more component bonding strength than isotropical conductive adhesive. This is because this adhesive bonds the component has a larger area than the previously used isotropic conductive adhesive. The fourth surface mounting technique is that we developed a method to solder components on aluminum conductor. As we all know that it is very difficult to solder components on aluminum conductor because aluminum has a very dense surface oxidized layer that grows almost immediately. And it's very thick and dense, so the solder flux used for copper conductors are not aggressive enough to remove this oxidized layer. So in this thesis, we developed a method to use a special ammonium-based soldering flux to solder components on aluminum conductor. And by doing so, we could enable aluminum as the main conductor material for electronic circuits. And because this technique requires a soldering temperature of 280 degrees, so it is only applied to flexible circuits made from aluminum and polyimide. The result showed that the contact resistance measured from the components mounted are low, and the component bonding strength was almost half as components soldered on rigid PCB. And that's why we also recommend this method to be used in implementing electronic systems. And I would like to give a summary to the surface mounting techniques that we have developed. The advantages of these techniques are it has proven that hybrid electronic system can be implemented with non-conventional materials, and low contact resistance can be achieved, which means we have a low signal or power loss on mounting joints. the result also showed that some of the surface mounting techniques support electronic systems that requires bending. And for the low temperature solder paste method and for the isotropic conductive adhesive method, we can upgrade them to a fully automatic mounting process with the necessary equipment provided. However, it is also seen that the components mounted using this method have a lower mechanical strength than rigid PCBs, and which means circuits manufactured from these materials and surface mounting techniques will have a low environmental endurance than rigid PCBs. Therefore, circuits made from these techniques are not recommended used in high temperature, high mechanical stress, or high vibration environments. Now, with the first two steps introduced, I now will introduce the step 3, where we have implemented two RFID reader antenna systems that works on different frequencies. And before we go into the details of the antenna systems, I would like to explain why do we choose RFID reader antenna systems. First, the reason obviously is also very obvious, that we need a demonstration of large area electronics on a system level. And we also would like to use the previously mentioned non-conventional materials and develop the surface mounting techniques. And would like to have an opportunity to integrate both digital and analog signals, especially high frequency signals. And such a large area large area reader antenna system can have the potential to perform large area RFID monitoring and positioning, where the principle is here that if we arrange antenna elements in a matrix and control this matrix with an industrial RFID reader and an external control unit, and we could periodically scan through every antenna elements and to see if there is an RFID tag on top of it, such as this tag can be only read by antenna element 3, 2. And in this case, the position of the tag is the same as the antenna element that reads it. And we can deploy these kind of antenna systems under the floor, such as under the floor of this room. The circuit topology of the two antenna systems are the same. It is called single pole 4-through switching network, initially SP40. The switching function is performed by having SP40 multiplexers arranged in different tiers throughout the system. The central component of the multiplexers are SP40 RF switches or SP40 analog switches. And these multiplexers are I2C addressed so that it can be controlled through an external control unit, which is shown here in the blue lines. And the terminations and loads of the switching network are antenna elements that works on different frequencies. And there are a few reasons why we choose this topology, because it is expandable, that the system can grow further like a tree, and and we believe it is a favorable feature for large area electronics, that it should grow, and it requires only one input port from here. And because of the multiplexing scheme that we can have similar characteristics on each channel. The first antenna system is an reader antenna system that works for 13.56 megahertz. It is manufactured from screen printing silver flaking onto a photo paper with components soldered using the low temperature solder paste. And the previously mentioned low DC resistance method number 1 was used for this antenna system. And it is a 1-tier SP40 switching network with 4 antenna elements. And the antenna elements are coil antennas that are matched to 50 ohms. And this antenna has an area of 135 millimeters by 135 millimeters. And here are some of the key measurements of this antenna system. It showed the antenna elements are well matched to 50 ohms by having low return loss. That was as low as minus 15 dB. And the loop antenna has achieved a Q factor of 6.0. However, compared to an antenna made from copper with the same dimension, that this is still quite low. And the multiplexers have low insertion losses, which is as low as minus 0.33 dB. And we measured the RFID passive RFID read range with different input power from 15 dBm to 33 dBm, where we have a measured range from 6.0 centimeter to 11.1 centimeter above the surface of the antenna system. And we also measured the RFID tag interrogation zones with different input power, which results are presented here. It can be seen that interrogation zones can be controlled by input power and heights. And if we use these 2 parameters wisely, we could avoid RFID interrogation dead zones on top of the antenna system. And it can be seen that we have very confined RFID interrogation zones, which are in the range of a few centimeters. And this is a good feature when it comes to RFID tag positioning. The second reader antenna system works on 867 megahertz, and it is a true demonstrator of large area electronic system. In this antenna system, we use aluminum as main conductor with a component soldered on aluminum. And this antenna system is a 3-tier SP40 switching network with the load are rectangular microstrip antenna elements. And in order to connect multiplexers on different tiers, we used microstrip transmission lines. And this is the experimental setup of this antenna system, that it has an area of 1.2 meters by 0.6 meters. The key measurement of this antenna system showed that the antenna elements are well matched to the resonant frequency, and the multiplexer has an insertion loss of 0.82 dB. The microstrip line insertion loss is minus 0.64 dB per meter, which means that the attenuation of the whole network is minus 3.3 dB, which means that the microstrip antenna element here will have 46.7% of the power that are from the RFID reader. And we measured the passive RFID tag read range of this antenna system. It showed that we have a read range between 2.3 meters to 4.3 meters with input power from 15 dBm to 27 dBm. And we also measured the RFID tag interrogation zones. It can be seen that the conclusion is similar with the HF RFID reader, that the interrogation zones can be controlled with input power and the heights of the RFID tags. However, unlike the HF reader antenna system, that the interrogation zone of this antenna element is quite wide, so which means that the interrogation zones formed by these 8 antenna elements will mostly overlap with each other. So in this case, it's not it's not an advantage for positioning accuracy. However, it is a good advantage for monitoring RFID tags over large areas. And then we also discussed a little bit about the system limitations with two objectives. The first objective is we want to discuss what is the maximum antenna system area, and the second one is to discuss the maximum numbers of antenna elements. And the essence of reaching these limits are to expand the SP40 switching network with more tiers and more antenna elements in a way that the system becomes so huge that the attenuation of this network also become large, that the power emitted by the antenna elements cannot power up passive RFID tags. And of course, a ground rule for the expansion is that we should have no RFID tag interrogation dead zones on top of the antenna system. And here is an example of how to expand this SP40 switching network. Because I don't have enough space here, so I only made it as 4 tiers with the blue dots, the SP40 multiplexer. And it can grow into all the dimensions like a tree. And there are 2 ways that we could reach to the limitation. The first one is to increase the SP40 network tier numbers, which has a direct relationship to the number of antenna elements. And the second method is to adjust the antenna elements density. In this case, we defined as 4 antenna elements per unit area. And here are some of the results that we have calculated. It showed that the limitations of this antenna system depends on the range of the RFID tag. For example, if we place a RFID tag closer to the antenna system, which means less power is needed from the antenna element, and which means it can tolerate more attenuation in the SP40 network. And if we could tolerate more attenuation, which means we could have more tiers and a larger area in the antenna system. So if we place the RFID tag only 1 meter away from the surface of the antenna system, we could have maximum antenna elements and area simultaneously achieved with multiplexer tier number 7 and antenna elements more than 16,000 and has a total area of 1,887 square meters. And in this setup, the antenna element density is 4 antennas per 0.46 square meters. However, if we increase the range, we find out that the 2 limitations should be discussed in different ways. Let's say if we place the RFID tag 4 meters away from the surface of the antenna system, then we can achieve the maximum number of antenna elements with a multiplexer tier number 6, and the number of antenna elements become 6,096. However, we only have a total antenna system area 487 square meter. However, if we are going for the large area, the maximum antenna system area, then we could have a setup that has a total area of 576 square meters, but only with 3 tier of multiplexers and 64 antenna elements. And here are the conclusions of this thesis work. So for this thesis work, we have demonstrated, we have successfully demonstrated a systematic approach from non-conventional substrate and conductor materials and to large area electronic devices. And we have achieved new material combinations to manufacture flexible circuits. And we also fabricated low resistance conductive tracks using conductive inks. And we also have proved that hybrid flexible circuits can be implemented using non-conventional materials with several developed new surface mounting techniques. And in the end, the large area electronics systems have been successfully implemented and characterized with system limitations discussed. The future works. I divide the future works into 3 steps also. The first step is materials and fabrications. And in the future, it would be nice to have an automatic or semi-automatic way to implement vias. In that case, we could achieve multi-layered electronic systems using non-conventional materials. And we can find new sintering and fabrication methods for the conductor inks to achieve even lower resistance. So they could be more suitable for high current applications. And for surface mounting techniques, that we could improve the technique we have, so they can be used for mounting components with a small package, such as a ball grid array. And with these 2 steps achieved, that we could have large area multi-layered electronic systems with functions more than RFID systems. And in the end, it could be an alternative, a good alternative, and even maybe replacing traditional rigid PCBs. Thank you. That's all.
Thank you, Tian.
So, now we will have a short break of about 5 minutes. Please do not enter the Zoom room because you will exit the Zoom room because you will not be able to enter again. But just stay tight, take a cup of coffee, go to the bathroom, and we will be back in about 5 minutes. Thanks.